In this example, we're given a circuit that contains a couple of storage elements, a capacitor and an inductor, and they cannot be combined, and we're being asked to compute the voltage across that capacitor after switching. So we have a switch in here, and we were told that that switch was closed for a long time, and then at time equals 0, it opens, and we're asked to compute what that Vc of t after switching. So I'll start off by writing the differential equation that describes the circuit that results after switching. And the way I'm going to do that in here is I'll clean it up here. So, well, after switching, the whole part in here doesn't exist. That's what we're left with. Okay, so we can now, for example, write a KVL equation, because you probably have recognized that this is a simple series RLC, like you can combine the 2 and 3 as well. But anyway, we can just say, we can write that, and what we'll end up with is negative Vc of t, okay, plus what we can say is this is the positive, this is the negative, and we can assume that the I of t is just flowing that way. This becomes positive, this is negative, this becomes positive, this is negative. Okay, and then we can say, well, this is 3 times I of t plus, well, that's V across the inductor. But just as a quick reminder, the VL of t, which is the voltage across the inductor, is just simply L times di of t divided by d of t, since I of L is the same as I. And we know that the L is just simply 1 because it's 1 Henry. So that is here, so we can just say, and just as a quick check, passive sign convention, we hit the positive, so positive here is okay. So that tells me that this simply here is di of t divided by d of t. So I'll write 1 here just as a reminder, this is the value of L, plus 2 times I of t, this is for the resistor of 2 ohm, equal 0. So we have written this equation in here, and this equation has I of t and the Vc of t, and so we have to write one in terms of the other. Either one is fine, but since we're looking for Vc of t and for initial conditions for later, you're going to find that it's a little bit easier now to convert I of t in terms of Vc of t. So just as a quick reminder, what we know is the following. We know that I believe I of t, which is the current flowing through the capacitor, is just simply C times dVc of t divided by d of t. But in this particular case, what we have is the current is going into the negative port. So what we need to do is we need to add a negative in here. That's what we have to do. And the C value is just simply 0.2. So I'll just write it in here. That becomes 0.2. So the I of t from a capacitor perspective is just simply negative 0.2 times dVc divided by dt. Okay, so let me just write that here. So I of t is just simply negative 0.2 dVc of t divided by d of t. So that's good because we can substitute it in here, we can substitute it in here. But also the equation has the first derivative of the I of t, so I'm going to take the first derivative of that. So the first derivative of the I of t divided by d of t is just simply negative 0.2 second derivative, okay, of Vc of t. So what we now do is, well, we'll keep Vc of t. Whenever we see I of t, we substitute it with that. That's specifically here and here. Whenever we have the first derivative of I of t, we just substitute with the second derivative in here. So that's here. So let's rewrite this equation. We get negative Vc of t plus 3 plus 2. I'm just going to add them because 3 and 2 are both multiplied by I of t. And what we multiply with is negative 0.2 dVc of t divided by d of t. Okay, plus I believe that will be the di of t, which is 1. Well, that will be negative 0.2, the second derivative of t in here, and that equals 0. And we can do a little bit of algebra, and what I'm after is I'll divide everything by negative 0.2 so that I'll get the second derivative coefficient is 1. So what I'll end up with is dvc squared divided by dt squared, and I'll say plus here, and that here, if we multiply, that's 3 plus 2, which is 5 times 0.2 divided by 0.2 as well. So we're going to multiply by negative 0.2 and divide by 0.2 to get rid of it. So it's just simply 3 plus 2, which is just 5. And that here is just simply dVc of t divided by d of t. And then the last one in here is just simply, I will have a negative 1 divided by negative 0.2, which is just simply plus 5 Vc of t equals 0. So this here is the first order or second order differential equation that describe this particular circuit after the switching, which is right here. And if you think about it, what we have is we have a forcing function that is 0, which makes sense because there are no sources after switching. So we don't have a particular solution. So because the solution we have discussed before is the following, the solution for that v, well, we called it x of t, but this now is v of t is just simply the complementary solution plus the particular solution. And well, I'm now confusing VC and complementary and VC as a capacitor, but as it turns out to be, in this particular case, there's no particular solution because this here is 0. So the input is 0. That means that I only care about the homogeneous solution, which is the complementary solution. So as it turns out to be, that VC of t is what I'm after. So what we need to do right now is we know what to do. There's no particular solution. We found it. So what we're going to do is write the characteristic equation for this differential equation. The characteristic equation tells me simply it is, well, the coefficient of that second derivative is just 1. So all I have to do is just tell you this is s squared plus 5 of s plus 5 equals 0. Okay, that means 2 alpha is just simply, remember, it's like we have termed these to be 2 alpha, and this one here, omega 0 squared. So 2 alpha is that way. That means alpha is just simply 2.5. And omega 0 squared is just 5. That means omega 0 is just the square root of 5. And the square root of 5 is approximately 2.24. And both cases are, by the way, rad per second or radians per second. Okay, so what you can do is you can either compute the discriminant delta for this fact, which is 5 squared, which is 25 minus 4 times 5, which is just simply 25 minus 20, which is just 5. It's greater than 0, or you can just tell me simply that alpha, which is 2.5, is greater than omega 0. So in both cases, what you can tell me is either here or either here, you can tell me, well, the response is overdamped. And if it's an overdamped, we know what the solution should look like. The solution actually contains the following. The solution, the complementary solution, VC of t, will just simply be k1 e to the power of s1 of t plus k2 e to the power of s2 of t. So what we need to do is we need to find what these two roots here, s1 and s2, are. And that is simple. We can just simply say s1 is just, I believe it will be the roots of this characteristic equation right here, okay, which is negative 5 plus square root of 5 divided by 2. And s of 2 is just negative 5, negative square root of 5 divided by 2. Okay, and that here will be the one with a positive. It will be negative 5 plus square root of 5 is negative 1.38. And this one here will be simply negative 3.62. So this is S1 and S2. All we have to do now is just tell VC of t is just simply K1 times e to the negative 1.38 of t plus K2 e to the negative 3.62 of t. And that is here in volt. That's for t is greater than or equal to 0. However, we still are missing a couple of things, which are K1 and K2. And then when we do that is by two initial conditions. So I'll redraw that circuit in here. So here's the circuit. So what we have said is the following. So the switch was closed for a very long time. And of course, in that particular case, what we have is the following. Because I'm going to compute everything right before switching. Because what I'm after is VC of t, so the VC right before switching is exactly the same as right after switching. Typically for initial conditions we care about 0 plus, but anyway, so that's what we have for now. And what I will do is I'll tell you the following. So this one here is just, we can replace it with a simple wire. Okay, so let me just do that here. That will be replaced by a wire. And this one here should be replaced with an open circuit because the capacitor is an open circuit. But what we can do is we can say the following: plus minus, this is VC of 0. Okay, we can say 0 minus or 0 plus, it's the same. All right, so we can compute that fact now, and the way we can do that is simply we can either do a source transformation on this, for example, and in source transformation then we can apply voltage division. So source transformation told me this is plus minus 4 times 5, which is 20 volts. That simply is 5 ohms. And then we have 2 ohms. And then what we have is 3 ohms. Okay, and the voltage that we're interested in is between here and here. That's plus minus VC of 0. It's the same voltage across that 3 ohms. So what we can say is VC of 0 is just simply 20 times 3 divided by 5 plus 2 plus 3. And that should be equal to 6 volts. Okay, So that's that. We can also compute actually the current, the initial current in here, I0 minus, for example. We can just call it I0 minus, which is the same as 0 plus. Remember, there was an inductor in here, so 0 minus or 0 plus for current is the same. We can compute that in here, and I can tell you that I of 0 is just simply, it is, well, I know the voltage across that 3 ohms, so all I have to do is just say the voltage 6 divided by 3 ohms, which is just simply 2 amps. Okay, so that's basically the initial current flowing through it. All right, so how do we use the initial conditions to find K1 and K2? I have found what the initial condition. Again, there was an inductor in here. I found what the initial current across it. There was a capacitor. I found what right before switching, right after switching. This is the same, and this is also the same. So what we can do is we can tell you, well, VC evaluated at 0 is just simply K1 plus K2, because what I've done is I substituted T equals 0 here, T equals 0 in here, so that is 1, that's 1, so K1 plus K2. But I know what VC of 0 is. I just computed it to be 6 volts, so I know that this is just simply 6 volts. So the equation I'm after is, this is the first equation actually out of 2. Now the second equation, what I will do is I'll take the derivative. Well, I know, well, the dVC of T divided by d of T. Well, that's the voltage across a capacitor. Well, hopefully you remember that that's C equals I of T as well. This is what we found out here. Let me just make sure that you see it. It's actually here, but of course we have the passive sign convention in here as well. So I need to put a negative in here. So this is actually the voltage, the dVC divided by dt is just simply the current across that capacitor. But of course, what we have in here is, because we have passive sign convention and everything in that equation, what we have is negative in here. And see, let me just make sure I rewrite it here for you so that you can see that. So what I will do is I'll just copy these ones in here, and we're just going to say that. All right, so let me just show you. So that's what we have in here. You can definitely ignore these here. Okay, so what we have is the following. That's what I'm after. I'm after the dVC divided by dt, but I know that actually it contains negative 0.2 and I of t in here. So what I'll do is I'll say dVC of t divided by d of t is just simply negative 1 divided by 0.2 I of t, okay? And that here is dVC of t divided by d of t is just simply negative 5 I of t. So now if I substitute t equals 0 in here and t equals 0 in here, what do I end up with? Well, I end up with negative 5 times I0, but I0 is just, I figured out to be 2, so that's simply negative 10. All right, so that's good. So I know that dVC of t divided by d of t when t equals 0 is just simply negative 10. Do I know what it is also for these? Yes, I can. I can basically take the derivative of that here, and that derivative will be k1 times negative 1.38 and so forth. So let me just take that. You can either look at the general solution I have provided, or you can just basically simply tell me, well, here's that equation. Take the derivative in here. So let me just write it in here. What is dVC of t divided by d of t? Hopefully you can see it. It's negative 1.38 k1 e to the power of t, or negative 1.38 t, okay, negative 3.62 k2 e to the negative 3.62 of t, but we'll assume that t equals 0 in here. By t equals 0, that means the exponent in here goes, or the exponent here goes away, so we'll end up with this equation in here. And this equation, we already know that it should be equal negative 10. This comes from here, okay, because this one here is the same as that. So what we end up with is, this is the second equation we end up with, okay? All right, so let me just highlight it with a color that you can see. All right, so this is what we have. So we have two equations to unknown. This is the first equation. This is the second equation. We should be able to compute what K1 and K2 are. And if you do, we'll end up with the following. So K1 will be just simply 5.23, and K2 will be just simply 0.77. So the total solution is just simply VC of t is simply 5.23 e to the negative 138t plus 0.77 e to the negative 3.62 of t. And you can double check it very quickly. If you substitute t is 0 in here, t is 0 in here, you'll end up with 5.23 plus 0.77. So the total will be 6 volts. And we know that initially we had a 6 volts across it. And if we wait for infinity, we know that there is no source in here. So in infinity, that V should be 0. Of course, if you wait for infinity in here, this will be 0, this will be 0, and the whole thing will be 0. Now you can take a look at the plot for that VC of t, and that's how it should look like. Remember, this is an overdamped response, so there should be no oscillation. So if you take a look at that, that's exactly what we have. So initially we have some sort of a 6 volts in here, that's what you see. Okay, and with time you will see it slowly reaches its value 0 in here. It sluggishly reaches it, and there's no oscillation whatsoever. That's basically what this equation looks like. So the x of t here is just simply v. It represents vc of t in here, and the forcing function is 0 in this particular case because that's what we have.